Welcome back, folks. We're going to use the source conversions that we talked about in the last video. We're going to use those to try to get down to a value of interest in a circuit. Okay? Not that practical. This is usually the point in the semester where a lot of people realize that maybe they should have bought 2 notebooks for this class, because you're going to end up redrawing the circuit a lot. I'm going to try to cut and paste as much as I can, but it's really a technique that involves combining things, converting them to reduce complexity, and then recopying the circuit over and over and over until you get down to something as simple as just applying Ohm's law to find the value that you're interested in. In reality, I use this technique to reduce the complexity of a circuit, but we are going to find a dead horse and just beat it as much as we can, so that we can practice the technique and see how to apply it over and over and over again. So I got an example, nice and small to start out with, and then we'll grow in complexity. I'm going to do 4 examples for you for this method. Okay, so I want to find I out, and I out's over here. So when I'm considering applying a source conversion, I have to go through a series of questions in my head. I have to say, is there anything in series that I can combine? Is there anything in parallel that I can combine? So that would be resistors, that would be voltage supplies when they're in series, current supplies when they're in parallel. Those combinations are the things that are really making the circuit simpler. Now, there isn't always a combination that you can make, and I think we found that when we were working some just resistor problems, just trying to reduce resistors. But if we can apply a source conversion, sometimes we can force some stuff to be in parallel or in series in a way that allows us to reduce the complexity of the problem. So with this problem, we're going to start out looking for I out. And the first thing I'm going to do is say, is there anything in series that I can combine? And the only things that I see in series are this voltage supply and R1 up here. So there are 2 components, they are in series. That's going to be useful to us because that is a Thevenin equivalent, but I'm not going to use it quite yet because I don't see anything else that's in series. Okay, I can't combine those directly. Is there anything in parallel that I can combine? So if you're really paying attention, hopefully you are, you haven't fallen asleep on me yet, you can correctly say that R3 is in parallel with R2, but I can't combine those, because if I combine those, I out gets lumped in to the parallel combination, and I'm not going to be able to tell you what portion of the current flowing through these 2 parallel branches is flowing through I out. So I got to be careful. Even if I can combine them, they are electrically in parallel, they share the same 2 nodes. I shouldn't do it because I'm going to lose this current. Okay, something similar is going to happen with voltages when things are in series. We got to be careful with that. We'll see that in a few examples as well. So if I can't combine those 2 because they're in parallel and nothing else is in series, then I have to consider conversions. And the conversion that I pointed out earlier, I said, hey, there's a voltage supply with a series resistance. So we're going to take that. Okay, that's a Thevenin equivalent, right? So there's my Thevenin. Maybe we'll make Thevenin blue. We'll see if the color coding works out. All right. And I'm going to convert that to a Norton equivalent. Okay, so copy the same circuit over. Let's see how much space I'm going to need for this one. Clean up our circuit a little bit. And in place of that Thevenin equivalent, I'm going to put a Norton equivalent. So I got to get rid of all of this stuff. And maybe it's going to be quicker if I do this. Okay. And the rest of the circuit acts as the load, so it stays the same. So the stuff that I'm converting is going to change, but the 12 ohm and the 4 ohm stay the same. They're still in parallel. I'm still finding I out through the 4 ohm. So make sure that you move that notation down. I cut and pasted it, so it, usually you watch me write this on a whiteboard. You would have seen me do that, but we got to make sure that stays in the same place. Okay, so we take that Thevenin equivalent and we draw a Norton equivalent. Okay, so we've got to get values for the Norton resistance and the Norton current. 21 divided by 4, if you remember from the previous video, is going to give us our current. So what is 21 divided by 4? It's going to be like 5 and 5.25. Okay, so this is 5.25 amps. Okay, and I got that from 21 volts divided by 4 ohms. Okay, the resistance, well, it just moves down. It's the same value, it's just connected differently. So it's still 4 ohms. I don't need to write a formula for that one. It's the same value. Okay, so that's the Norton equivalent of that Thevenin equivalent. And then I connect the load back to it. So the rest of the circuit, I usually redraw that by hand, but since we have it, might as well do a little cut and pasting, right? Okay, so now we look at this circuit, and we say, is there anything in series? And the answer to that is no, nothing's in series in this circuit. Is there anything in parallel? Yep. Can I combine them without losing a current, right? So in this case, I can combine the 4 ohm over here and the 12 over here. So I'm going to go ahead and combine those. Neither of those have I out, so I'm not losing that current. So that's pretty safe to do. Okay, so we redraw it again. Okay, and I'm going to combine these two. They're in parallel, so this is going to be 4 in parallel with 12. Let's keep the nice one, right? It's no longer R2. But it's going to be 4 in parallel with 12, and that's equal to 3 ohms. Okay, so we're getting there. We're good. At this point, hey, look, it's a current divider. You could go ahead and apply the current divider if you wanted to, if you're comfortable with that. So we took a problem that might have taken a little bit of analysis, nothing outrageous, and we got it down to a current divider. That alone should tell you that we're reducing complexity. But like I promised you, I'm going to beat this horse as much as I can so that we can apply these source conversions over and over and over again, hopefully so that you're gaining some level of comfort. No horses were harmed in the making of this video. Okay, is there anything in series? Nope. Is there anything in parallel? Yeah, the 3 ohm and the 4 ohm are in parallel, but I still can't combine those because I'll lose I out. So I have to consider conversions. I don't see any voltage supplies, so that tells me there's no Thevenin equivalence. I do see a current supply, and there is a resistor in parallel with it. Okay, so this is our Norton equivalent, and we're going to convert that to a Thevenin equivalent. Okay, so let's do this, and actually we're gonna get rid of a lot of stuff here, right? So we get rid of our Norton equivalent like that, and we reattach a Thevenin equivalent. All right, so we're going to go find those values, but ultimately we're just going to connect it back up to the rest of the circuit, thinking of the rest of the circuit as our load. Okay, making this conversion, we take I Norton, 5.25 amps, and we multiply it by R Norton, so that's going to be 3 ohms, 15.75 volts. Okay, that's the Thevenin voltage right there. R Norton is 3 ohms, and R Thevenin equals R Norton, so that just moves down here. No longer in parallel, now it's in series, but the value is the same. And everything's hooked back up to where it was. Okay, let's see here. Is there anything in series we can combine? Now, I couldn't combine this with something else in parallel because they're going to carry 2 different currents, and we're not going to know the proportion of current flowing through R3, but these are in series. And if we think back to the introduction to resistors being in series, really any components being in series, they're going to carry the same current. Okay, so we can combine these, and the current through the what's going to be a 7 ohm resistor is going to be I out. Okay, so we're going to combine those two. We get something that looks like this. Right, here's 3 plus 4 equals 7 ohms, and I out is still correctly labeled here, and we've got 15.75 volts there. Okay, and I think I said it either at the beginning of this video or the end of the last. I'm going to try to do this until I get it down to an Ohm's law problem. And here's Ohm's law. I know the voltage across the resistor, 15.75 volts, and we're going to divide by 7 ohms. And what do we get for that? That's kind of a funny one. I thought it worked out nicely, but not so much, not horrible. 2.25 amps. Okay, so I didn't have to do any kind of fancy analysis, but I had to be really good at spotting equivalent circuits, when things were in series and when things were in parallel. I had to be really good at redrawing the circuit. But let's see what happened here. We started out with a problem that had 2 meshes. Oops. All right, this was 2 come on. 2. There we go. 2 meshes. And 1, 2, 3 nodes. So not a horribly complex circuit at all. We converted it, and we ended up with 3 meshes. Oh, we went the wrong way there, right? And 2 nodes. Okay, so maybe this one would be better for nodal analysis. We only have 1 unknown in that case. So we could get that down to a single KCL equation. Okay, converting it further, we ended up back at 2 meshes. And 2 nodes. Okay, getting better. And then down here we ended up with 1 mesh. Hey, that's pretty cool. We could have used mesh analysis on that single mesh if we wanted to. And we ended up, well, we went back up with 3 nodes. Okay. And then finally we ended up down here at 1 mesh and 2 nodes. Okay, anywhere along this path you can change your plan and you can apply mesh or nodal when you're comfortable with the size and complexity of the circuit. We're going to make these more complicated. I'm going to do 2 more with only independent supplies, but they're going to get far more complicated. And then I'm going to throw one at you with a dependent supply because I like to. Okay, you got to learn how to do that. So I better give you at least one example. Okay, so hopefully you're comfortable with how we're applying these. I'm expecting that you need some more practice. That's what we're going to get in the next 3 videos. So stay tuned and good luck.